So now we want to look at the situation where there are multiple forces acting on an object. And we know that the forces are vectors, so that means we need to add the vectors together to get the net force on an object. So in our example here, let's say this is 3 strings pulling on a puppet or something. We have a force of A that is 7.2 newtons at 33.7 degrees south of east. Force B is 12.6 newtons, and it's 18.4 degrees west of north, and force C is 7.3 newtons, and it is 15.9 degrees south of west. So we want to know what is the net force on the object. So we can do some trig and find the x and y components of the forces, as we do here, and then we add them together to get the net force. So yeah, we can do this. We'll do this in a bit, but what we really want to do is we want to be able to visualize the forces. So what we want to do is we want to draw free body diagrams. A free body diagram is when we draw all of the forces acting on an object. So our 3 forces from before, so A, B, and C, are all shown here, and we can add them together. We can do the graphical addition, where this becomes A, and then B, and then C, and then we can add them together and see that the resulting force, so the net force, is going to be pointing up and to the left. So the idea is that you want to consider the forces acting on an object. So we're going to do a lot of this, and drawing a free body diagram is one of the best ways to try and understand the dynamics of a system. So to solve a question like this, you're going to have to find the angles. So for force A, it is 33.7 degrees south of east. So here, if we kind of draw this in here, we've got this angle is south of east. So that means we can consider that to be negative 33.7 degrees. In the case of B, so this is 18.4 degrees west of north. So north is at 90 degrees. So then we would add this angle of 18.4. So that gives us the angle of 108.4. And then for C, then it is 15.9 degrees south of west. So west here is 180 degrees. So we add our, 15.9. And so that then gets us to 195.9 degrees. So the idea here is we want to convert these angles into the counterclockwise angle from the east, or counterclockwise from the x-axis. So once we've done that, then we can find our x and y components. So notice we picked these sort of odd angles so we could get our x and y components to be integers. And so then finally, if you want to come up with a resulting vector, then you add them together. And so we do that here. And this adds up to be negative 5 in the x direction and plus 6 in the y direction. So the same thing we got from our graphical analysis. The important point here is that when we draw a free body diagram, we want to put all of the forces acting on our object, and then we do it, with usually the way I do it is just a little block like this. And so then the idea is that you add each force on an object. So if we're doing projectile motion, so we have our force going down. So we call this weight 1e. So that means that we have a force that should be going straight down. And so this, in that case, is the only force acting on an object. Now the thing is, let's say we put our object and we put it on a table. So why isn't it accelerating? Well, in this case, we've got the weight force is acting on our object, but there's also something called a normal force, and that is basically the force of the table that is pushing onto the object. So those two balance each other out, so the net force acting on our object here is 0. So another thing to keep in mind is that just because there are no net forces on an object can still be moving. So a good example of this is terminal velocity. So we have a parachuter that jumps out of a plane, and at first they do accelerate, but the air resistance increases as the faster they fall. So eventually the force from the air resistance is equal to the force of gravity, and then the parachuter falls at a constant velocity. So they're falling pretty fast, something like 120 miles per hour, but they're undergoing no acceleration because their speed isn't changing. So our free body diagram here for our free falling person, it's going to be weight 1e, And then we've got, I don't know, we'll call this friction 1 air for the air resistance. And those two forces are exactly equal, so that means that our parachuter is falling at constant velocity. So you kind of have a question like this to do about free body diagrams, with the key being that if your forces are balanced in both directions, then that means there's no net acceleration. And if there is an unbalanced force, so if you have a force like this, so I don't know, he's got a rocket, and so he's firing to the right. Here, our person is not doing constant velocity. Here they have a net force to the right, so they're going to accelerate to the right. All right, so good luck with that question, and next we're going to look at the second law of motion.